All right, welcome back. Who's excited to do some more calculus review? We did not get through all of the spring 2025 exam last night because my iPad's battery died, but I am charged to 97% right now, so we should be good to finish up that spring 2025 exam and maybe look at one of the other ones if there's time and interest. As always, send me questions in the chat, or you can also email me. So, we left off with question 15. Which of the following is the Riemann sum using right endpoints with n rectangles that approximates the area between y equals x squared and the x-axis from 1 to 4? The general formula for a Riemann sum is it's the sum from I equals 1 to n of f of a plus I times delta x times delta x. This is using right endpoints. And delta x is b minus a divided by n. In this case, that's 4 minus 1 divided by n, or 3 over n. And so the sum is the sum from I equals 1 to n of f of 1 plus I times 3 over n times this delta x, which is 3 over n. And then we should evaluate the function. The function is f of x equals x squared. So look at the sum of 1 plus I times 3 over n squared times 3 over n, which is option C. The next question asks us to evaluate the integral of this function from 0 to 4. So I see this area below the x-axis, and then this area above the x-axis. So the integral is going to be minus the area of that first triangle, which is a base of 1 and a height of 2, plus the area of this triangle, which has a base of 2 and a height of 2, plus the area of this rectangle, which is simply 1 times 2. All right. The next question asks us to use the fundamental theorem of calculus part 2, which tells us to integrate something from a to b. We find an antiderivative, plug in a, plug in b, and subtract. We're integrating f prime of x, so an antiderivative is f of x. So I plug 3 and 1 into f of x. F of 3 is 8, f of 1 is 2, 8 minus 2 is 6. Good afternoon, Jawless Love. K McCollum, what would it look like if it was integrating the integral backwards? So, do you mean like integrating from 4 to 0, f of x? Because in that case, that would be just the opposite of the integral from 0 to 4. Switching the bounds just has the effect of throwing in a minus sign. So this would simply come out to negative 3. Right, the indefinite integral of 1 over x. We looked at this yesterday. This was one of the integrals in the definite integral dominoes. The indefinite integral dominoes activity, antiderivative of 1 over x is ln of the absolute value of x, plus c, of course. There is a plus c whenever we are doing an indefinite integral. There is no plus c when we are doing a definite integral. If you write 6 plus c, you're saying it could be 6 plus any number, which really just means it could be any number. But it can't be any number, it is just 6. Which of the following expressions computes the area between this parabola and this straight line? So the integral, or the area, is the integral of one of the curves minus the other one. So we have 2 things to figure out. The first one is which of the terms is f and which one is g. The second thing we need to figure out is what are the bounds. I can find the bounds by equating these y values and solving. If I subtract an x over and subtract a 3 over, I get x squared minus 2x minus 3, which should factors of 3 that subtract to 2, that would be 3 and 1, so it's going to be x minus 3, x plus 1. So x is negative 1 or 3. It turns out we didn't actually need to do that, just because this was a multiple choice question, and every single option has an integral from negative 1 to 3. But if this were not a multiple choice question, this is how you would find the bounds. Now, which function goes first? So it's either option A or C. This is adding the functions. These each only have one of the 2 functions. So it's A or C. Which one comes first? There are many different ways to figure this out. What I think is the simplest is just to sketch a quick curve, a quick graph of these 2 curves. The first one is a parabola with a positive leading coefficient, which means it opens upward. The second is a line. Now, if I'm not worrying about where exactly the line is, but I know it's not below the curve, because then they wouldn't be asking me this question, because there is not there's not a finite amount of area between these 2 curves. I need the line to be up here in order for there to be an area. Also, we solved this equation and found that there are 2 places where the line and the parabola intersect. So that's another reason I know that it's not down here. So it's got to look something like this, and that means that the line is above the parabola. So it's going to be this option. The equation for the parabola, the other one. The equation for the line minus the equation for the parabola. Another way to figure this out without sketching a graph would just be to plug in an x value somewhere between negative 1 and 3. So at x equals 0, the x squared minus x is 0, and at x equals 0, the x plus 3 is 3. So you can see that the line has a bigger y value, at least at x equals 0. But that's also going to be the case for all x values between negative 1 and 3. Okay, we're going to evaluate g prime of 2. Yes. If this is g of x, then g prime of x is the derivative of that integral This is exactly the situation that the fundamental theorem of calculus part 1 tells us about. The fundamental theorem of calculus says that I take the upper bound, substitute it in for t in the integrand, but then if it was just an x up here, I would just get f of x and I'd be done. But since it's not just x, the chain rule also requires me to multiply by the derivative of the x cubed. And then g prime of 2 is going to be f of 2 cubed times 3 times 2 squared, which is f of 8 times 12, and f of 8 is 3. So we get 36. Okay, we are looking at the graph of lowercase h, and we're going to be thinking about the function uppercase h, which is the accumulation function of lowercase h. So what is capital H of 3? Capital H of 3, if I just write out the definition, it is the integral from 0 to 3 of h of t dt. So it's all of this area, but negative, and all of this area, which counts as positive, makes a positive contribution to the integral. Oh, sorry, I went to 4. I went way too far. There we go. And we could think about the areas of the square and the triangle, but I can just see that these two triangles have the same area, so that they cancel out, and I'm just left with this negative 1. And at what x values does capital H have a local minimum? Okay, so the thing to note is that lowercase h is the derivative of capital H. That's the fundamental theorem of calculus. When you differentiate capital H, which is this accumulation function, you get the integrand with the upper bound of x substituted in. That is, you get h of x. So what's happening here is we are being asked about a function, but we're being shown the graph of its derivative. So where does it have a local minimum? When we look for local minima or maxima, we start by finding the critical numbers. Critical numbers are the places where the derivative is 0 or undefined. But remember, I'm talking about critical numbers of capital H, not lowercase h. I'm looking for places where h prime is 0 or undefined. But h prime is little h. So I'm not looking for places where the slope is 0, because I'm already looking at the graph of the derivative. I'm looking for places where that derivative, the derivative of capital H, is 0. So that happens at -1 and at 2. Now, the first derivative test tells us that a local minimum occurs when the first derivative changes from negative to positive, because that means the function is going from decreasing to increasing. So I'm looking for a place where lowercase h goes from negative to positive. That happens at x equals 2. All right, we made it to the short answer. I'm going to draw the graph of a function defined on 0 to 2. Okay, so let me draw some axes. such that f of 0 is -1. There we go. F of 0 is -1, and f of 2 is +1. But f of x is not equal to 0 for any x in the interval from 0 to 2. So the point of this question is that if the function were continuous, the intermediate value theorem would tell me that it has to have a value of 0 at least one x value. You can't continuously get from -1 up to +1 without crossing the x-axis. But they didn't say that the function has to be continuous. And it's very easy to draw a discontinuous function that never takes on the value 0. There are many, many different ways to do that. And then let me just point out, when they say make sure to label your graph, that just means, like, label your axes as x and y, and most importantly, label these x values and y values, so that I can see that this point actually is at 2, 1. Okay, for what value of k is this function continuous on the interval from -infinity to infinity? Alright, so the first thing to notice is that we're only really thinking about what happens at x equals 1. Because for values of x greater than 1, the function is this quadratic function. Quadratic functions are polynomials. Polynomials are continuous. And for x values less than 1, we have a straight line, which again is a polynomial, so it's continuous. The only place where something weird could happen is at x equals 1. So what does it mean for f to be continuous at x equals 1? It means that the limit as x approaches 1 of f of x needs to be equal to f of 1. Okay, what is the limit as x approaches 1 of f of x? Because this is defined piecewise with a piece to the left of 1 and a piece to the right of 1, I need to compute the two one-sided limits. The one-sided limit as we approach 1 from the left is well, since I'm only looking at values of x less than 1, in that region, f of x is equal to 2x plus 1. And that's a polynomial, so I can directly substitute, and I get 3. To the right of 1, we have x plus 1 squared minus 1, which is again a polynomial, so I can directly substitute. 2 squared minus 1 is 3. And these are equal, so that means that the limit as x approaches 1 is 3, because we're approaching a y value of 3 from both sides. F of 1, on the other hand, is k. So if the function is going to be continuous, I need 3 to be equal to k. So these problems can be a little confusing, but the way to approach it is to just think, what does it mean to be continuous? Let me write out the definition of continuity at 1. I see that it's a limit being equal to a function value, so I just think about what the limit and the function value are. The function value is k, and the limit I can compute by doing two one-sided limits. Equation of the tangent line to the graph of f of x equals 2x plus 3 over 3x minus 4 at x equals 7. Okay. I'm looking for the tangent line. That's an equation of a line. I need... sorry. Supersum 1, would I be able to solve by setting them both equal to each other? That's a great question. And you're thinking that because there are problems that look similar where you have to set the left and the right limit equal to each other. The point... I assume you're referring to the left and the right one-sided limits. The point is that in other problems, there might be k's involved in not just the f of 1 term, but in the first and last cases. And so when I do this limit computation, I might get expressions that depend on k. And then I set those equal to each other because in order for the limit to exist, I need the left and the right one-sided limits to be equal. That's why we set those equal. We need the left and the right one-sided limits to be equal for the overall limit to exist. In this case, when I computed these, there were no k's involved here. There's nothing to... I don't need to adjust the value of k to make 3 equal to 3. I just found that the left and right one-sided limits were already equal. Yeah. So there are two different flavors of this kind of question. There could be a question where you have to choose the value of k to make the left and right one-sided limits equal. In this case, however, they're already equal. We're choosing the value of k to make sure that the function value is equal to the limit. What is something that is not a polynomial that you could not directly substitute the limit into? Just as a general rule of thumb, if you can directly substitute into an equation and you don't get something like division by 0, if you actually get a number, it is almost always legitimate to use direct substitution. I would have to come up with an example where you have an equation and you try direct substitution but it's not valid. I would have to use like a piecewise equation or something. But almost every function that you know about is continuous everywhere in its domain. Polynomials, rational functions, trig functions, inverse trig functions, exponentials, log functions, and any sums, differences, constant multiples, products, differences, exponentials, any combination of composites. Any combination of continuous functions is continuous everywhere in the domain of the function. So I guess to answer your question, I would have to like write down a piecewise function where you wouldn't be able to directly substitute. All right, so tangent line. That's a line. I need two pieces of information to find the equation of a line. I need the slope, and I need one of the points on the line. Or I need two of the points on the line, and then from there I can find the slope. In this case, we're talking about the tangent line to a function, and the slope of the tangent line is given by the derivative. So I'm going to use the quotient rule to differentiate this 2x plus 3 times over 3x minus 4. And that gives me the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. If your instructor didn't teach you the mnemonic device for remembering this, if you refer to the numerator and denominator as high and low, and if I use the expression d to represent taking a derivative, this is low d high minus high d low. Draw the line and square below. Now I want the slope of the tangent line at x equals 7, so I need to plug 7 into the derivative. 3 times 7 is 21. 21 minus 4 is 17. Seven times 2 is 14. 14 plus 3 is 17. And 3x minus 4, once again, when x is 7, that comes out to 17. So on the top, I get 2 17s minus 3 17s. That is minus 1 17. Divided by 17 squared, this is minus 1 over 17. So that is the slope of the tangent line. I also need one of the points on the curve, but of course I obtain the y value at x equals 7 simply by plugging 7 into the equation of the function. And this comes out to 17 over 17, which is 1. Now I use point slope form, which says that the equation of a line with slope m going through the point x1, y1 is y minus y1 equals m times x minus x1. So my equation is y minus 1 equals minus 1/17 times x minus 7. You do not need to simplify or rewrite that equation in any other form. All right, derivative of sine of x to the x. We've seen this trick a number of times throughout calculus. When you have an expression with a variable in both the base and the exponent, and if you're trying to do something like take a limit or a derivative, it's helpful to take the natural log. Now I can't just take the ln of this because that would change the expression that I'm working with. So to get around that, I'm going to set y equal to this expression, y equal to sine of x to the x. So I'm looking for dy dx. And then I can take the ln of both sides of the equation. The point of the natural log, the reason it's helpful here is that the exponent comes outside of the natural log. So I end up with x times ln of sine of x. And now I differentiate both sides with respect to x. On the left side, I get 1 over y times dy dx. On the right side, I need to use the product rule. The derivative of x is 1. And then in the second term, I leave the x alone, and the derivative of ln of sine of x is 1 over sine of x times cosine of x. Okay, so I have 1 over y times dy dx equals ln of sine of x plus cosine of x over sine of x is cotangent of x. It would be absolutely fine to leave this as cosine of x over sine of x. As you saw in the indefinite integral dominoes activity, sometimes it was preferable to have the function expressed in terms of sine and cosine rather than expressing it as a single trig function. So it's not even that one of these is simpler. It just doesn't matter which format you write this in. The last thing I need to do to find dy dx is to multiply both sides by y. And then to remember that y is sine of x to the x. Substitute that back in. And there is our answer. It doesn't even fit in the answer box. Oh, wait. This is not the answer. Because they wanted the derivative at x equals 2. Sorry, pi over 2. So I'm going to substitute pi over 2 in. And this is actually a case where instead of cotangent of x, I would rather just have cosine of x over sine of x, because I don't know what cotangent of anything is. I know how to find the values of sine and cosine. Okay, sine of pi over 2 is 1, and 1 to the pi over 2 is 1. Again, sine of pi over 2 is 1. Cosine of pi over 2 is 0. Ln of 1 is also 0. So the answer is 0. That was a lot of work just to get 0. All right. Would points be taken away if you did not simplify the pi over 2 all the way through? You mean if you just wrote this? I don't know. There would definitely be some debate among the calculus instructors. On a free response question, if this was worth 10 points, I would definitely take off a point. I'd give you a 9 out of 10 for not simplifying it all the way. Out of 3 points, taking off a whole point is... it would feel a little bit harsh. I definitely recommend simplifying this. We want to see that you know how to evaluate sine and cosine at these important angles like pi over 2. But I would say there's a decent chance that we'd still give you the 3 out of 3 if everything else was good. No promises, though. All right, where is this function concave down? So a function is concave down when its second derivative is negative. So I need to compute the second derivative, which means I need to compute the first derivative. The first derivative will be x to the 4th plus x cubed. And the second derivative will be 4x cubed plus 3x squared. And since I'm going to be setting this equal to 0 to find when this expression is positive or negative, I'm going to go ahead and factor this anyway. It's always easier to solve an equation when it's in a factored form. I see a greatest common factor of x squared. So I can pull the x squared out, leaving 4x plus 3. If I set 0 equal to x squared times 4x plus 3, x has to be 0 or minus 3/4. Now, when is this expression negative? I'm going to make a little sign chart. I've got negative 3/4 and then 0. Those are places where the derivative could potentially change, or the second derivative could potentially change sign. I like to just write out all of the pieces of the expression when I'm making a sign chart and think about them individually and then think about how they combine together. So we've got an x squared and a 4x plus 3. X squared is going to be positive no matter what I plug in, except 0. 4x plus 3, that's a line with a positive slope, so it's negative up until the point where it is 0, and then beyond that it is positive. The second derivative is these two things multiplied together. Positive times a negative is negative. Positive times positive is positive. So the second derivative is negative when x is less than negative 3/4. All right, Ralphie's running along a straight line path with a velocity given by this graph. Is Ralphie's displacement from her starting position equal to her total distance traveled from 0 to 2? So what's happening is Ralphie has positive velocity initially, meaning she's moving, let's say, forward, but slowing down until she stops, and then runs backward for a little while. Negative velocity, slows down and stops, and then continues moving forward, speeding up. So her displacement is not equal to her distance because she was going forward, but then turned around. We're only looking for from 0 to 2, so she was going forward, but then stopped, and then came back. So just to make up some numbers that are not correct for this problem, if she went 10 meters forward and then 5 meters back, her displacement would be 5 meters because she only ends up 5 meters away from where she started. But her distance traveled would be 15 meters, 10 forward plus 5 back. So displacement is not equal to distance when the velocity is sometimes negative. When the velocity is sometimes positive and sometimes negative, that means you're going in opposite directions at different times. Some of that distance that you travel cancels out when we think about the displacement, but not the total distance. All right, definite integral, find an antiderivative, evaluate it at both bounds, and subtract. E minus 1/2. All right, find all critical numbers, and we're going to classify them as local minima or maxima or neither. critical numbers happen when the first derivative is 0 or undefined. The first derivative will be 0 if the numerator is 0. But the first derivative will be undefined if the denominator is 0. This is the easy one to forget about. Critical numbers happen not just when the derivative is 0, but when the derivative is undefined. So there are two critical numbers here. To classify these as local minima or maxima, I'm going to make a sign chart. Which will split at -1/2 and 0. And f prime of x is made up of a 2x plus 1, and in the denominator a 6x to the 2/3. Two x plus 1 is a straight line. It's with a positive slope, so it's negative until it's 0, and then it's positive. 6x to the 2/3. Well, remember, x to the 2/3 means the cube root of x squared, or equivalently, the cube root of x squared. Either way, you can see that because we're squaring, we're only going to ever end up with something positive. So at x equals -1/2, the first derivative changes from negative to positive. Negative to positive, the function is going from decreasing to increasing. That's a local minimum. At x equals 0, the derivative goes from positive to positive. So the function is increasing, it levels off, but then it goes back to increasing. That's a stationary point, but it's not a local maximum or minimum. Inflection points. So inflection points happen where the second derivative changes sign. So the function goes from being concave up to concave down, or vice versa. It's not just a point where the second derivative is 0. The same way that local minima and maxima don't always occur at every point where the where the first derivative is 0. I'm still going to look for places where the second derivative is 0. But I'm going to, again, have to make a sign chart and consider whether each one of those places actually is an inflection point or not. So the second derivative was x minus 1 over 4x to the 5/3. And once again, a critical number could happen not just where the second derivative is 0, but also where it's undefined. The second derivative will be 0 if x is 1, and the second derivative will be undefined if the denominator is 0, which happens when x is 0. Azul, aren't endpoints also critical numbers? No. So endpoints we never consider to be critical numbers or local maxima or minima. What you're thinking of is that a function's absolute maximum or minimum value could occur at an endpoint. So if I were looking for absolute extreme values, I would want to make sure to plug in not just the critical numbers, but also the endpoints. So let me make a sign chart again. We have an x minus 1, and then in the denominator we had a 4x to the 5/3. X minus 1 goes from being negative to positive at x equals 1. The x to the 5/3 is going to be negative when x is negative and positive when x is positive, because the 5/3 exponent means take the cube root of x to the 5th, or the cube root of x to the 5th. And both taking a cube root and raising to the 5th power preserve the sign of x. If x is negative, its cube root and the 5th power will both be negative, unlike that 2/3 power, where the numerator of 2 means squaring the integer. So overall, my second derivative goes from positive to negative at x equals 0, and it goes from negative to positive at x equals 1. So both of these x values do, in fact, have inflection points. But now when we talk about inflection points, they didn't just say the x value of an inflection point. A point is a point on the graph. It's an x value and a y value. So we should make sure to give the full coordinate pair. My function was 9 x to the 1/3 x plus 2. So 9 times 0 to the 1/3 times 0 plus 2. And 9 times 1 to the 1/3 times 1 plus 2. I'm just plugging my x values back into the original function to find the y values, to conclude that we have inflection points at 0, 0 and 1, 27. Is it possible for an endpoint to be a local maximum or a minimum as well, or just the absolute? The way that our textbook defines local extreme values, we would not consider an endpoint ever to be a local maximum or a minimum. You might be thinking of a situation kind of like this, where the points at the end do look like local extreme values. We just, as a matter of terminology, we just don't call it a local extreme value if it occurs at an endpoint. The book's reasoning, and I disagree with this personally, but we stick with what the textbook says just so that no one's getting confused if they're reading the textbook. Or at least that you're not getting confused because we're telling you a different thing in class. All right, and this is, and why am I saying I disagree with the textbook? Like, it's not. Why is there not just a correct answer? Because we're talking about a definition. We choose the definitions, but then we have to live with the consequences. So the point that the textbook wants to make is that a local extreme value should be bigger than everything else nearby, and it doesn't make sense, according to the textbook, to talk about being bigger than everything else nearby when there aren't even any y values on the left side to compare it to. Anyway, I don't want to dwell on this. The point is that for this class, we do not consider endpoints to be local extreme values. But you absolutely do need to consider them when you are looking for absolute extreme values. All right, definite integral. So I want to find an antiderivative. If you remember last night, we talked about 3 different methods for finding antiderivatives. Method 1 was just to recognize this as the derivative of something. And I don't recognize this immediately as the derivative of something else. Method 2 was to try to simplify or rewrite the integrand. I do not see any way to do that. The third method was U substitution. And this looks like an excellent candidate for a U substitution because I see an expression, the x squared plus 8, and I also see its derivative, which is 2x. So when I make the substitution, the 2x dx becomes du, and the square root of x squared plus 8 becomes the square root of u. 1 over the square root of u is the same thing as u to the minus 1/2. It's going to be easiest to find an antiderivative if I rewrite this as a power of u. And then the antiderivative is going to be u to the 1/2 divided by 1/2 plus c. That's 2u to the 1/2, or 2 times the square root of u, and then I'm also going to need to substitute the value of u back in. U is equal to x squared plus 8. So here's my antiderivative, and that means that the definite integral from 1 to the 2 square root of 2 by the fundamental theorem of calculus, part 2, it is this antiderivative evaluated from 1 to 2 root 2, which means I plug in the bounds, and subtract. 2 root 2 squared comes out to 8, because it's 2 squared, which is 4, times root 2 squared, which is 2. So it's 4 times 2. And then the 8 plus 8 is 16. And over here, I just have 1 plus 8, which is 9. 2 times 4 minus 2 times 3 is 2. Now there is another way that you can organize all of this work. It's not really fundamentally different, but if you don't want to bother converting back to x at the end, if you don't want to find an antiderivative and then do the definite integral, you can kind of combine it all together if you convert the bounds. So there was a reason I didn't write the bounds here. It's because if I wrote the 1 and the 2 root 2, that would be wrong. Because 1 and 2 root 2 are x values, but when I have a du, these values are to be understood as u values, not x values. So I can just convert the whole integral to an integral with u, as long as I also convert the bounds. What do I mean by that? Well, u is equal to 1 to x squared plus 8. So when x is 1, u is 1 squared plus 8, which is 9. And when x is equal to 2 root 2, u is equal to 2 root 2 squared plus 8, which is 16. So I've rewritten this as the integral from 9 to 16 of 1 over root u du. And the nice thing about this is that I have fully converted to u, so I never have to go back to x. So I just find my antiderivative, which, once again, I'm going to rewrite that as a u to the minus 1/2. I'll find my antiderivative, which is 2u to the 1/2. I evaluate it from 9 to 16, which means plugging in 16 and 9, and evaluating, and subtracting. And it, of course, comes out to 2 once again. If you look at this closely, you'll see it. It is exactly the same calculations happening either way that I write this out. It's just a matter of personal preference. All right. A box manufacturer wants to create an open-top box by cutting square corners from a 9x9 sheet of metal. What value of x maximizes the box's volume? Okay. The advice that I always give with related rates or optimization problems is to start out by drawing a picture. But we already have a picture. We have 2 pictures, in fact. So we can just move on to writing down an equation that models this situation. The volume of the box is going to be the length times the width times the height. So I just need to figure out what the length and the height are. So the length of the box is going to be that segment in the unfolded piece of material. And then the width of the box is this segment. And the height of the box is that piece, which I guess would be this or this. It doesn't matter which one. So how long is this? Well, this is 9 minus x and minus another x. So it's 9 minus 2x. And this also is 9 minus 2x. And the height is x. They've already marked that for us. So the volume is length times width times height. I'm looking for maximum or minimum values of this function. So I want to find all the critical numbers. Critical numbers happen where the function's derivative is 0 or undefined. So I want to find dv dt, or sorry, dv dx. If I wanted, I could expand this all out before I differentiated. I have a feeling that it's going to be easier to solve if I leave it factored. I will have to use the product rule and the chain rule, but that's okay. So the product rule says I should differentiate the first term and multiply that by x, and then I should leave the 9 minus 2x squared alone and differentiate the x. That was the product rule. Now how do I differentiate this? Using the chain rule, I get 2 times 9 minus 2x. That's the power rule. I'm pulling the 2 down and dropping the exponent to 1. But then I also multiply by the derivative of the inside function, which is negative 2. So I get minus 4x times minus 2x, 9 minus 2x plus 9 minus 2x squared. And both of these terms have a 9 minus 2x. So I can factor out a 9 minus 2x, leaving a minus 4x and a 9 minus 2x. And then 9 minus 2x minus 4x is 9 minus 6x. So finding the derivative was a little more involved in that I had to use the chain rule and the product rule. But the nice thing was that it made it really easy to factor this out because both terms had a 9 minus 2x. So I pulled that out, and now I have my derivative in factored form. I made this point a couple of questions ago that it's important to remember that critical numbers happen when the derivative is undefined. So we should always think about that, but that doesn't happen here. This is a quadratic. There's no value of x that makes this undefined. So the critical numbers will only happen when this thing is 0, that happens when x is 9 halves, or when x is 9 sixths, which is 3 halves. Now that we found the critical numbers, where did the minus 6x come from? Yeah, so after I factored out this 9 minus 2x and one of these 9 minus 2x's, I factored that out, I was left with the minus 4x, and then I was left with the other 9 minus 2x. And when I combine these together, I have 9 minus 4x minus 2x, and the minus 2x and the minus 4x combined together to give me a minus 6x. Now, if there's anything that's still unclear about how I did any of this, let me know. So now that we have the critical numbers, we should think about what the domain of this function is. Because the way that we go about optimizing a function depends on what kind of interval the domain is. If we're optimizing on a closed interval, that's the ideal situation, because I know that I know that absolute extreme values always occur either at critical numbers or at endpoints. So all I have to do is plug in all of the critical numbers and the endpoints and see which x value gives me the biggest or the smallest y value. If I'm optimizing on an open interval or all real numbers, the situation is a little bit more complicated. I'm going to have to think about local extreme values, and in general it can actually be pretty tricky, but we try to limit the problems we give you to situations where there's only one critical number. Because if you're on an open interval, and if there's only one critical number, then if it's a local minimum, it's also the absolute minimum. If it's a local maximum, it's also the absolute maximum, if there's just one critical number. Here, I would say the domain is Well, what's the smallest that x could be? They definitely cannot be smaller than 0. Can x be 0? I would say yeah. It would be a very silly thing to do, to make a box and not cut any of the corners off and then not fold anything up. You would have a box that's just the bottom. It has no volume. It's not a very good box. But it's not physically impossible to do, like trying to cut a negative amount of the box would be. It's not physically impossible, and it doesn't cause any issues mathematically with this function. I have no trouble plugging an x value of 0 into that equation. So even though it's silly to think about the volume being, or the x being 0, which causes the volume to be 0, because it doesn't cause any mathematical issues to include 0, I do want to include 0. And I want to include it because then I have a closed interval. And closed intervals are the easiest kind of domain to optimize a function over. What's the biggest x could be? The biggest it could be is if the 4 pieces that we're cutting out if they completely split the sheet of metal into 4 pieces. So you remove everything, and then there's no box. So it also has a volume of 0. You could do it. It'd be very silly, but you could do it. And the biggest value of x then would be 4.5. That's 9 halves. Because right, there's half of the 9 centimeters, there's half of the 9 centimeters. And again, plugging 4.5 into the equation doesn't cause any mathematical trouble. So the domain of this function is going to be the closed interval from 0 to 9 halves. Which means to optimize the function, all I need to do is evaluate the function at the 2 endpoints, 0 and 9 halves, and also at all of the critical numbers, which are 3 halves and 9 halves. But 9 halves was already the endpoint, so I only have 3 things to plug in. And we already talked about why the volume is 0 if x is 0 or 9 halves. Right, if you plug in x equals 0, that's going to make this part 0, so the whole thing is 0. If you plug in 9 halves, this is 0, this is 0, so you end up with 0. If I plug in 3 halves, though, I'm going to get something non-zero. I'm plugging x equals 3 halves into my volume equation. So I get 9 minus 3 squared times 3 halves, which is 6 squared, or 36 times 3 halves, which is 54. 54 is the biggest of these 3 numbers, so that is the absolute maximum possible volume. All right. If I wrote this all out on the exam, this problem, this would score 9 out of 10. So, who can tell me why this solution would lose 1 point? It needs units. Yes, bury the B. Anytime that you're talking about something with physical quantities, you have to include units. It didn't say that you need to include units, but it doesn't need to say that. By the final exam, by the end of the semester, we just expect that you know that you need to include units. We're talking about a volume, and the relevant dimension here was being measured in centimeters, so the volume is centimeters cubed. I thought math people don't care about units. No, yeah, in the abstract, right? We're just doing math. The units don't matter, but we are. I think not all of you taking this class are math majors. Probably a good number of you are taking this class because it's required for your major, which might involve doing something out in the real world. So we want to train you to think about how to apply mathematical tools to real world problems, and that does involve caring about the units. So that concludes the practice exam from spring 2025. If you have questions about any of the problems that I went over, let me know. Do you have to say that you're using the extreme value theorem? In general, if you're using a theorem, it's a good thing to say it. Are you talking about in this problem? Because in an optimization problem, what I wrote here is perfectly fine. If the domain were an open interval, you would have to probably write some more. You'd probably have to make a sign chart to justify that you find a local or a local maximum or a minimum. You would also need to say something about how there's only one critical number, if that's the reasoning that you're using to conclude that you have an absolute minimum or a maximum. But for this kind of problem, showing me very clearly that you are evaluating the function at all of the critical numbers and endpoints, that to me, you have demonstrated understanding that that is how you determine the maximum value on a closed interval. So I don't need you to say that on a problem like this. If you were writing this out in written homework, or you were somewhere that you wanted to present a nice, clearly explained solution, it would be good to say why. To explain the reasoning in a little more detail. But on an exam, you have less time, so we don't expect you we don't hold you to quite the same standards that we would on written homework in terms of justifying everything in detail. That was a long answer. Hopefully that answered your question, Zone Ranger. I just got an email. Oh! Yeah. You're asking me to do question 29 from the 2019 practice final exam. And I remembered you'd sent me the email yesterday. I was going to make sure to do that. But before we move over to that exam, are there any other questions about this one? And I guess if you have questions about the 2019 or the 22 exam, now would be a good time to send a message in the chat or email me. Let me know which problems you'd like to see. Okay. So 2019, question 29. Okay. Suppose a rover lander is exploring one of the 67 moons of Jupiter. Oh my goodness, that is so many moons. The rover is launched upward from the top of a 9-foot cliff. The velocity of the rover is minus 2t plus 8. So we want to find the total distance the rover traveled from t equals 1 to t equals 5. Okay. So the rover is launched upward. There is definitely gravity on all of the moons of Jupiter, even if it's less than the gravity we have on Earth, so it's a pretty safe assumption that the rover is going to fall back down to the ground. So it's going to go up, and then it's going to go down, and that means to find the total distance, I'm going to have to think about how far it goes up, but also then how far it goes down. So to do that, right, so it's going up and then it's going down. I want to maybe figure out at what time it stops going up and starts falling back down toward the ground. So I'm going to set the velocity equal to 0 and find what time that happens at. Okay, so that happens at time 4. 4 seconds, if I want to include units. If I wanted to be really thorough, I should be including units everywhere, but it's fine as long as you just put the units in the final answer in each part. Okay, so from time 1 to time 4, it's moving up, and then from time 4 to time 5, it's falling back down. So the total distance is, I'm going to use an integral to find how far it goes. If I know the velocity, not 4, but 5. The total distance, it's tempting to say it's the integral from 1 to 5 of the velocity. You accumulate the velocity, you find out how far it goes. That would actually not be the distance, that would be the displacement. If I want to find the total distance, I need to make sure that, I need to take the absolute value. I need to consider speed instead of velocity, because whether the rover is moving up or down, it is still traveling some distance, and I want to add up all of that distance. But this is easiest to do if I split this into 2 integrals. So I'm going to think about how far it goes when it's moving up from time 1 to time 4, and then how far it goes when it's falling from time 4 to time 5. And the point of this is that from time 1 to time 4, the velocity is positive. From time 4 to time 5, the velocity is negative. So when the velocity is positive, the absolute values don't do anything. The velocity is just 2t minus 2t plus 8. But when the velocity is negative, the absolute value flips it from positive to negative. Flipping it is the same as multiplying by -1. Now I can just evaluate these definite integrals using the fundamental theorem of calculus. Okay, so that's minus 16 plus 32 minus 1 minus 8. I'm distributing that minus sign. Plus 40 minus 25 minus 32 plus 16. A lot of stuff cancels out, which actually I didn't expect it to, so I'm kind of concerned that I might have dropped a minus sign somewhere. Minus 9 plus 15. Yeah, this isn't right. 2t minus 8 on the second integral. Oh, yeah. Minus 2t plus 8 is the same thing as 8 minus 2t. I didn't actually change the sign. Two t minus 8. Thank you, Zone Ranger. That's a good catch. All right. Now the things don't cancel out, which is a bummer, but that is what I expected. Okay, so 16, that makes 16, and then minus 1 minus 8 is minus 9. 25 minus 40 is minus 15. Minus 16 plus 32 is 16. 16 minus 9 is 7. Minus 15 plus 16 is 8. Is 1. So we should get 8. And now I do need units. The distance, we were talking about feet. So 8 feet. Can someone who's got the answer key pulled up, the solutions, can you confirm whether 8 is the correct answer? I don't love this question because I really wish that they had put part B first, because it would involve quite a bit less writing. It's a lot easier to do part A if you've already done part B. So part B asks you to find the position function. So position, which I'm going to call S of t, is going to be well, it's position is an antiderivative of velocity. Velocity is minus 2t plus 8. So the position function is going to be minus t squared plus 8t plus some constant. It's an antiderivative, but I could throw on any constant here and still have an antiderivative. How do I find that constant? It's because I know that at time 0, the position is 9. So the constant is 9. The position equation is minus t squared plus 8t plus 9. And the reason that this makes part A a lot easier is you still need to find when the velocity is 0, but then you just think, how far did the rover travel between times 1 and 4? And subtracting those positions might give me something positive, it might give me something negative. So I'm going to make sure it's positive by taking absolute values. And then how far did it travel between times 4 and 5? I'm going to find those. Find those positions, subtract them, and make it positive. And it'll come out to the same thing. Which hopefully is 8 feet. Okay, part C. Determine the time it takes for the rover to land on the ground below the cliff. Well, I'm saying that its position at the start, at the top of the cliff, is at 9 feet. So it reaches the ground when its position is 0. I'm going to set the position equal to 0 and solve. This factors as time t minus 9 times t plus 1, so t is 9, or negative 1. Negative 1, of course, doesn't make sense because it started moving upward from the top of the cliff at time 9. So after 9 seconds, it will reach the bottom. The integral gives 10 feet? Oh no. Anyone see where I went wrong? Minus 1 plus 8? Oh, wait. Oh! Yeah. Wait, right here. So that should be plus 1 minus 8. Ah! So then we're only subtracting 7, which leaves 9. And so we get 9 plus 1, which is 10. All right, thank you. There we go. Oh, yeah, Zone Ranger mentions another really good way to go about this problem, which is if we look at a graph of the velocity, it's 8 minus 2t. That's a straight line with a slope of negative 2. So if we look at the velocity graph, the distance traveled is going to be this area minus that area. The area of this this first triangle is 1/2 times base times height. The base is 3 because it goes from 1 to 4. The height is 6 because if I plug in 1 for the velocity, I'll get 8 minus 2. And then the other triangle has a base of 1 and a height of 2. So I get 18 times 1/2, so 9, minus 1. Somehow I've once again gotten the wrong... Oh, yeah. The displacement is 8. But the total distance is going to be the total area here. So 9 plus 1, which is 10. So honestly, this is probably an even better way to go about it than doing all of this. And then question D, determine the maximum speed at which the rover travels from its liftoff until landing on the ground. The maximum speed. So my gut feeling is that the maximum speed is going to be at time 9, at the very end when it hits the ground. Because it starts off moving up, but then it slows down, and then it speeds up. When it reaches the same level as the top of the cliff where it began, it should have the same speed as it had at the beginning, but then it's going to keep accelerating as it approaches the ground. So that's my physics intuition, is it should be at time 9. How would we figure this out mathematically? Well, if I want to know when the maximum of the velocity is, or the maximum value of the speed, I should think about when the derivative is 0. That means the derivative of velocity. But that derivative of velocity is just negative 2. There are no critical numbers for the velocity function, which means that the maximum or minimum value of velocity is going to happen at an endpoint. So either 0 or time 9. So if I plug in 0, I get 8. If I plug in 9, I get 8 minus 2t minus 2t plus 8. which is minus 18 plus 8, or minus 10 feet per second. So the maximum speed is a positive 10 feet per second. We have a suggestion to maximize the square of the velocity. Yeah, that's a really nice way to handle maximizing something with an absolute value. As instead of doing that, you maximize the square of the thing. I think for the purposes of a Calc 1 exam, we would be quite happy with you just finding the extreme values of the velocity and then saying that the maximum speed is that 10 feet per second. But that maximizing the square of the velocity is a really nice trick. I'm curious, turn one Nat Pagel, did you see that trick somewhere? Like, how did you come up with that idea? It's a really cool idea. And in the meantime, does anyone have any other questions from this exam or the 2022 one that you'd like me to do? Same as optimizing the distance. Yeah, if you want to maximize the distance. There, I guess it's because you want to avoid the square root. That could be annoying. So maximizing a distance is the same thing as maximizing a distance squared. There's a really nice problem that I saw in a physics class once that used this same sort of idea. So just something fun for you to think about. If you throw an object upward, if you throw it up at a very steep angle, its distance from you will increase for a while, but then that distance decreases. Whereas if you throw it at a lower angle, the distance from you actually always is increasing. So the problem is, what is the maximum angle that you can throw the object at so that the distance from its starting point is always increasing? That is a fun problem. It's very challenging relative to a Calculus 1 course. But if anyone is bored and wants a cool, fun optimization problem, I highly recommend that. Suggestions for any questions on either of these practice exams? Is there another practice exam we can do? On Canvas, you'll find three: the spring 2025, the spring 2022, and the fall 2019. If you mean other than those three, no, I don't believe I have any others. I'm trying to remember if there was another practice exam or if there was like a practice midterm 0 sort of thing. Let me check. I don't remember if this thing I'm imagining actually existed, or if I'm confusing it with something else. I'm looking back in Canvas for the fall semester. Sorry, I should be looking in Canvas for last spring to see if we made something available. I don't see it there. Let me check my email. I'm not finding it. So again, I don't know if this actually ever existed. So I think it's just the 3 exams that you can find on Canvas, which is better than calculus students have had the last few semesters before the spring 2025 ones became available. There used to just be 2 practice exams. But yeah, if you've done all 3 practice exams, and if you feel good about all the material, I think you're ready to go for tomorrow. Just make sure that as you're doing the practice exams, if you get a question wrong, you're not just looking at what the answer is, but you're also trying to really deeply understand why you got the question wrong. Just like conceptually, what was it that you didn't understand? And if you go through all 3 practice exams and find all of your mistakes and dig deep and find the root misunderstanding for all of the questions that you got wrong, that should be plenty of preparation for the final exam. Alright, I'm going to sign off in another minute or so unless there are any more requests for questions. So if you've got any problems you'd like to see, let me know in the next 45 seconds. Alright, well thank you all for being here. I hope this was helpful. I wish you the best of luck on tomorrow morning's exam. I'll see probably some of you bright and early at 7:30 a.m. or a few minutes before. And I hope the rest of your final